seriously outlined in the report.
Why is it not displaying on the screen? What did you do? I just didn't.
We are interested in top-down, high-level influence to so-called lower-level stereo depth discrimination. In particular, I'm trying to provide evidence to you today that when the top-down recognition information helps for the stereo depth discrimination, the second point first is when the top-down influence provides contradictory expectations from the physical stimulus information from stereo depth, recognition performance will be impeded. In contrast, when object recognition can facilitate stereo discrimination, then the discrimination performance is going to be improved. So that's the two main points I'd like to convey. To start with, let me use a simple example. In this figure at the center, assume that this is presented in stereo, in depth. And the question is whether the 3D distance between the two green points closer together, or the 3D distance between the two red lines closer together. Okay. Of course, this is a basic stereo discrimination task, and we all, as human subjects, can have certain threshold performance. Now, I can turn this, hopefully at the beginning, a relatively random configuration into a meaningful working human figure. And then I ask you the question again, same question, same stimuli. Now, assuming at the beginning you didn't recognize this is a human figure, now after the working stimulus, you have recognized whether your stereo depth discrimination will change the law. That's the question. So in other words, put it simply, whether in this example, whether the red forearm is relatively longer in 3D or the green forearm is longer. Our real question is, as we said in the title, how recognition of a human figure influences stereo depth discrimination. Well, why are we doing this? The first point we try to do is to demonstrate the active role of high-level shape recognition onto lower-level stereo depth discrimination. We try to demonstrate such influences indeed there. Secondly, we try to provide empirical evidence for the validity of Bayesian prior probability distributions in the approach of Bayesian approach in visual perception. We try to provide data to show that Bayesian prior indeed can explain the result. So those are the 2 points. And of course, we are not the first people to do this. Guido, Sinha actually did related, similar experiments. So on the left, it shows in stereo again the human walker, and the human subject could either look in the z direction, or 0 degrees, or in the x direction, 90 degrees away. And this is just a normal human walker. In contrast, we also did distortion, just moving the dots, each dot, z orbit, along the z dimension. And of course, if you look along the z direction of the human walker figure into v is pretty much unchanged. However, if now you turn 90 degrees away, the figure is much distorted. So they, by manipulating the 3D distortion effect of this human figure, can try to study how that influences our judgment in terms of whether the stimulus is a human figure. And they're using a rating pass. So this slide shows if it's just a regular human walker, then regardless if you're looking along the Z direction or any other direction, it is pretty much a good human walker. On the other hand, if you distort the human walker along the Z dimension, but if you look at the stimulus along the Z dimension, the result is that that's irrelevant. Distortion doesn't change the thing. Human subjects still rate this figure as good a human figure as undistorted. And this is a control we use random patterns. Okay. So the result is essentially saying, so long as you distort along the Z dimension, recognition of this particular walker object is not changed. The perturbation of the 3D text information theory is irrelevant. We take, in this study, a slightly different approach. We actually hypothesize that this top-down instance of meaningful human walker, rather than in the earlier study, completely overriding, overwhelming the 3D text theory information, this top-down influence actually has a finite but measurable influence. Hypothesis number one. And along the same line, we try to establish that, in fact, the 3D information provided by theory of text information is important, is relevant in object recognition. So, how do we do it? Here is the summary of how we take our experiment in 3 steps. We, at the beginning, before any subject, any naive subject, could recognize this stimulus as a human walker, we measure the basic stereotypes, discrimination performance of these subjects. We then provide this walker movement to allow subjects to recognize that now this is a human walker. And then we come back to repeat step 1 and to remeasure the human performance and see if there is any performance change from step 3 to step 1. And here are the details. So in step 1, we present actually static, upside down figure to naive subjects. And from Johansson's original study, we know that naive subjects typically could not recognize this stimulus as a human figure. And the task is whether the 2 red dots are closer in 2D than 3D, or whether the 2 green dots are closer in 3D. And we measure psychometric curve performance for this particular task in this step. In order to control for any possible bias for 2D, we actually present in all trials the red dots 2D distance and the green dots 2D distance. They're always equalized. So subjects cannot rely on the 2D distance difference to do the job. Only the 3D distances of the 2 pairs differ. The second step is we just provide the subject with this upright short movement of the walker, and all subjects have no problem recognizing that this is a meaningful walking figure. And in step 3, we basically repeating step 1, except we turn the figure upside down, we turn the figure upright, so that it is easier to recognize that this is a human figure. Again, just to remind you, the task is whether the 2 green dots are further apart in 3D or the green or the 2 red dots. And this is the result in terms of the psychometric measurement. The horizontal axis is the 3D distance difference between the 2 pairs of dots. And the vertical axis is subject's performance in terms of accuracy. And this just curves out the subject's performance. the dotted curve is the subject performance in step 1, which is, we call it session 1, and the solid curve is the subject performance after recognition in step 3, we call it session 2. And apparently from this plot, you can see that the subject's performance, in fact, after recognition, is getting worse. So in order to reach, for example, 80% performance correct, the 3D distance difference has to be larger in the second stage, session 2. Okay. So from this result alone, we make an inference that the prior expectation of equal length, or approximately equal length, of the two forearms hurts actually stereo depth discrimination. I should also mention that this effect is a conservative measure because just in case some subject could indeed recognize from step 1, session 1, this is an inverted human figure, then it only makes our possible effect smaller. Okay, so it doesn't hurt our statistically reliable result. In fact, so far among all our naive subjects during the debriefing after the experiment, nobody recognized the first step that student was a human figure. And after the movie being shown, all subjects could indeed recognize that was a human figure. But of course, we need to do control experiments as typical psychophysics. First thing we did was, well, to see if the effect I just showed you had anything to do with recognition. So the simple control here is we repeat step 1, measuring the performance of stereo depth discrimination. And step 2, we just skip it. We do not show that movie. And then in step 3, we measure that again. So if there is any learning effect unrelated to recognition performance, then we can see that. Okay. And here is the controls group of subjects, 17 subjects. And the effect, actually the difference from step 3 to step 1 is actually not relevant. And in fact, the difference in session 2 and step 3 is actually slightly improved. Okay, so it is slightly going in the opposite direction. So the previous result cannot be due to just repeated measure from step 1 to step 3. And we take another control experiment. If our hypothesis that the higher level expectation of the two forearms are about equal, that was the influence that hurts the performance, then if that holds water, if we change the distance measurement from the elbow to the hand, for example, to the hip point, and there the distance, constant distance constraint is much weaker, if it still exists at all, then we should expect very different results. And that's the rationale of second control experiment. So we use hand hip as opposed to hand elbow dot pairs and repeating all the 3 steps without recognition, moving, and with recognition. This slide just shows the stimulus in step 1, upside down, hand hip, and upright hand hip performance. And we needed to control for the task difficulty. So on average, this control experiment 3D distance is equal to the first experiment. Okay, so we make sure we control for that. And here is the experimental result. It's completely opposite first experiment. In fact, in this case, when the constraint of expected equal length of the two forearms is gone, subject performance is improved from session 1 to session 2. In other words, from step 1 to step 3. Meaning, when you can recognize that this is organized, meaningful human walker, then we hypothesize that the reference frame we use is more accurate. At all the points, not just only the green pair and the red pair, but all the data are meaningful. We may be able to have a more accurate reference frame to do such stereo discrimination tasks. This is the inference we made. Familiarization with the recognized human figure improves the representation accuracy and improves discrimination. And this, in fact, is consistent with an earlier study by Tani before, because running out of time, I'm going to run this through very quickly. This shows also human walker, but at each point, instead of a dot, they show the gabor. This gabor is, as a function of time, changing its phase, temporal phase. And the human subjects need to judge whether all these gabors change their phases at the same time or with different phases. This is basically the result. When it is upright human figure, the performance is much better than inverted human walker, in this case, the walker. This summarizes all the three experiments, one experimental prediction, two control prediction results. The threshold change from session 1 to session 2, the threshold being at 75% correct performance. Essentially, it says the same story, so I'm not going to go through that. But let me just to conclude. We have evidence, hopefully you agree with me, that a top-down influence from shape recognition to lower-level stereo depth discrimination. And this influence could be both inhibitory and facilitatory, depending upon how the influence interacts with the stimulus physical information. Thank you very much.